Hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Step on inside, and the video may be uploaded out of sequence for those who've been watching in its current form. However, inside my Big Ideas Math IM2, Integrated Math 2 playlist, it should be in the proper order. This is the Chapter 3 Test and Cumulative Assessment portions of the textbook. If you check the description section down below, you'll see a PDF of these exact pages. They are in sequence with one another. And then you also find PDF of the graph paper, and you'll also find the timestamps for each problem if you're trying to find something specific. Now, it's been a minute since I've seen the problems out of the textbook for this. Not that I can't do them, but I forget if there's something specific that they ask for that we want, but expects a lot of graphing. This is what this chapter is all about. Graphing out of vertex form, standard form, intercept form. I apologize if I ever call it factored form. That's also a way because you factor them. And what else will we have to do? That's the part I can't remember, the other things that we're going to have to do. So sit tight and enjoy your flight as we go on and look at several questions here to begin with. This is the Chapter 3 test portion of it. After it is the cumulative assessment, which means it also covers Chapters 1 and 2, and I think, as well as 3. And then I think it has more multiple choice kinds of questions at that point, but for now it's graphing, fill in the blank, whatever it is. So questions 1 through 3, we are going to indeed be graphing. Graph the function, compare the graph to f of x equals x squared. So on number 1, remember, compared to f of x equals x squared, we have h of x equals 2x squared minus 3. Now let me begin with the transformation parts, describing and comparing them, and I'll go ahead and type these ones out. The 2 is your a value in this case, and this is, I'm treating this like standard form. You can also treat it like vertex form. There's either one or the other, or as this is where the book differs from how I teach it. The book just calls this only merely a vertical translation, but there's also a stretch. So you vertically stretch f of x by a factor of 2. Everything's going to be twice as big. And you also vertically translate, I don't know if you have to say vertical, but 3 units downward. The negative 3 is what's going to do that. So when I create this graph, and I'm going to go ahead and use the tall graphs for these. I assume that those will probably work out, be more appropriate for these parabolas. But when I graph this one here, what I want to do is, or what I'm going to do is I start with the translation. I start with the translation portion because everything I do is in relation to my translation. What I mean by that is this. 3 units down will be my vertex compared to an f of x graph of just x squared at the origin. And now everything is going to be doubled. Normally I go over 1 up 1, over 2 up 4, over 3 up 9, over 4 up 16. You go up the square amount that you go over. However, we will double those amounts we go up. Instead of going over 1 up 1, we'll go over 1 up 2. And parabolas reflect across the axis of symmetry, in this case the vertical line that goes through the vertex. Instead of going over 2 up 4, I'm going to go over 2 up 8. 2, 4, 6, 8. Now remember, the minus 3 is already taken care of. Everything is 3 lower than it would have been as long as I go in relation to the vertex. Instead of over 3 up 9, I'll go over 3 up 18. Now 18 up from negative 3 is 15, so up here. And there's the reflection bit. And that's what this parabola will look like. Try and make a smooth curve. Go through those, at least better than what mine probably will end up doing. I get an undo button. You just have a silly eraser on your pencil. Ha 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 ha. Okay, I'd probably fare better off if I just reflected that thing over, but I'm going to do my best. Okay, so there's the graph, there's the description, there is the answer. I don't have to graph f of x either, right? Doesn't look like I do. That's number 1. Okay, number 2. G of x equals negative 1/2 x squared. Okay. So, no k value or c value, no translations this time. There are vertical components that are affected here, however. The first one is dealing with the negative itself. That's what's going to make your y values opposite of what they would have been. You take 1/2 x squared, then you make them negative. You change their signs. That's called a reflection. You reflect across or over, I think they say. I'll say over. They say a reflection in, but reflection over the x-axis. You reflect over the x-axis. That's going to be the part that makes that thing negative. This graph will flip over that way. And then there's a vertical, not a stretch, but a compression, or a shrink, as they'll probably call it. Vertically compressed by a factor of 1/2. Of a 1/2. Vertically compressed by a factor of 1/2. So we'll go ahead and sketch that graph. The vertex is at the origin. On this one, we will start at 0, 0, just like f of x equals x squared would have been. Now, instead of going up, we'll be going down. And instead of going 1, 1 to 4, 3, 9, we'll be taking half of those values. And I'm going to fit as many as I can. So over 1, down half of 1, that's 1/2. Reflect that. Over 2, down half of 4, that's 2. Over 3, down half of 9, which is 4.5. Over 4, down half of 16, which is 8. Over 5, down half of 25, that's 5 squared. Half of 25 is 12.5. Over 6, down half of 36, which is 18. My graph only goes down to negative 17, but hey, I'm going to get something near about. It's right there. So 18 down. I like the 1/2 graphs when it comes to showing some width and being able to draw a good looking curve. The last one that had a 2 was very tall and very hard to come up with what that curve would kind of do. But I always say for these ones, this shows its character. It shows its character. So it's a reflection. It flipped it over, and it's compressed more so. It looks wider in your eyes because I only go as tall or short as the window fits, but everything's compressed. The y values are half the height that they would have ordinarily been. That's number 2. I'm kind of all out of room on that page. Let's move forward. Number 3. Now, this looks like vertex form for me, so I'll treat it as vertex form. And by the way, I'm going to go back to number 1 really briefly here. I'm not going to do anything new on the problem other than give it just a little revisit, a little nudge. You have one of two ways you can look at this thing. You can either look at this in standard form, which I'll get into more later, but this is ax squared plus bx plus c, and you can find ways of using that vertex that way. Or you can look at it as vertex form like this. Excuse me. Because the book doesn't really see them this way. They teach these formed after they use the ax squared plus c form, but either of these will reveal that your vertex is indeed at 0, -3 if you do the right work or you have your understanding of that, but either of these would have done exactly that. And I point that out just for number 3, we are in vertex form this time. Your vertex form a times x minus h quantity squared plus k. This vertex is at -1, -1. Opposite this h gets you that k. So with that in mind, there are still things to describe for this stuff. You are vertically compressing this graph the same way that was last time. And remember on the last problem, it was a -1/2. I still put 1/2 for the compression. The negative did the reflection portion. This one doesn't have a reflection. We are going to translate 1 unit left and 1 unit down. I'm not going to say horizontal and vertical and stuff. Left is horizontal, down is vertical, so I'm good. Okay. Let's go for it, right? Right? All right, so 1 unit left, 1 unit down gives us our vertex there instead of at the origin. And we'll do that 1/2 stuff as we just did last time. Over 1 up 1/2 of 1. Over 2 up half of 4. 2 squared. Over 3 up half of 9. Over 4 up half of 16. I wish they used a different number set, right? So excuse me, sorry, 8 is half of 16. But I wish they used a different number. We just did 1/2. They should have used 1/4 or something. 5, 6, 7, 8. I think that's right. Over 5 up half of the 25, which is 12.5. And over 6 up half of 36, which is 18. This time it actually fits right up there because that's 17. And 17 is 18 away from -1. -1 is the minimum height of our vertex, that y value. So here's our graph, not reflected over like the last one, but there are translations to be had with this graph having been in vertex form. There's a tableless approach to drawing that graph. I hope that made some sense from here. Okay, those are numbers 1 through 3. Let's move forward. Number 4, consider the graph of the function f. I might copy and paste this one over. Give me a second. By saying I might, meaning that's what I'm going to do. Okay. Let's do some things with that. Part A. Find the domain, range, and zeros of the function. Okay. The domain is about how far left and right this graph goes. It goes left and right forever. That's my all real numbers symbol. The range for this graph is how far up and down this graph goes. It has a maximum of 8, which it includes 8, and it goes down forever after that. We say y is less than or equal to 8. That is the domain and range. The zeros are another way of referring to the x-intercepts, the values of x, when y equals 0. Those zeros are 3 and 7. You solve for x when the function equals 0. Now, I don't know what the function is yet, and I'm sure that's one of the questions they're going to ask us here in a bit. B, here it is. Write the function f in standard form. It's interesting that they bring up standard form for this, given that well, it's not interesting but we're going to have to come up with it in vertex form first. That's not necessarily always true, but it's a way that I'd recommend that we go about doing this, because we're not going to use a system of equations format for this. Now, there are two different ways that we can come up with this. You can come up with this out of what I would call factored form or intercept form. But out of this factored form, we know that we can make an equation that says y equals a, oh, they said f, so let's use f of x. F of x equals a times, and then your two intercepts, and I think that's where the zeros kind of kick in. So x minus h times x minus k, excuse me, not h and k, p and q. If your zeros are 3 and 7, then x minus 3 and x minus 7 are your two factors. Now we can substitute a special xy that's not one of these points on the graph, such as this one. We can substitute a special xy into here and then come up with the a value as a result of that. When y is 8 and x is 5, we can figure out what the a value that would be that we would have for this. So we get a times 2 times negative 2, and a would be negative 2. So the equation, now I'm going to do this in vertex form as well, but the equation would then therefore be f of x equals negative 2 times x minus 3 times x minus 7. We need to still get this in standard form, which means we need to expand this thing through distribution, which means I will be foiling here next. I'm going to do negative 2 times, through FOIL, this would be x squared minus 7x minus 3x, that's negative 10x, then plus 21, and that's f of x equals negative 2x squared plus 20x minus 42. I guess that means the y-intercept is negative 42. All right. That was a lot of work for that one. Let me scrunch that up into here if I'm able. Just kind of move this part over. Sorry about that. I'm also going to do this out of vertex form. So that's one option. Standard form, factored form. Vertex form. Out of vertex form, I will then instead use the vertex and one of those points to make an equation, which would then say f of x equals a times your x minus, now I'm talking about the vertex. This is now my hk, 5 and 8, hk, and I can use this, say, as an xy. But x minus 5, quantity squared, plus 8, my hk. Now I can substitute an xy into here, such as 7 for x and 0 for y. I could also plug in 3 for x with 0 for y. As 7 minus 5 is 2 and 3 minus 5 is negative 2, when you square either of those, you do get positive 4, which is what's about to happen here. A times 2 squared plus 8. I'm going to subtract that 8 over. I should have done that the previous step. Negative 8 equals 4a, a equals negative 2. That sure looks familiar as the one that we got right there, right? So we got negative 2 either way using that. But now out of vertex form, if I wanted to, do this thing and fill it out, I'd be doing f of x equals negative 2 times x minus 5 squared plus 8. We return x and y into their x and y forms. And then we expand that guy out. That would be negative 2 times x squared. This is a perfect square trinomial. X squared minus 10x plus 25 plus 8. That's negative 2x squared plus 20x minus 50 plus 8, which is negative 2x squared plus 20x minus 42. Now, there's a third way of doing this, sorry, here are the two answers. They're both the same thing, whether I use vertex form or factored form. There's a third way of doing this using standard form, and you're like, why didn't you do that first? Because it involves solving a system of 3 equations, and 2 of them actually might not have been too bad to find as far as letters go, but we haven't done that. We haven't done that together in any sort of way with videos and such. I don't even know if we've touched systems of equations outside of just doing it on if you're ahead with me on chapter 4, section 4.8, I believe it was. But even then, we're not using a system of 3, so I wouldn't do that there. So these are the 2 methods I would be proposing to you: factored or intercept form or vertex form. That's part B. I'd still have to keep going on this problem, so let me kind of copy and paste this guy over to work on a part C. So part C, compare the graph to g of x equals x squared. Well, I like looking at the vertex form of this thing because I like to talk about the translations with the vertex. So first of all, as this thing did flip over, you do reflect over the x-axis. There was a vertical stretch. We got an a value of negative 2, so vertically stretched by a factor of 2. And then we also translate. We're going to translate 5 units right and 8 units up. So I'm kind of, like I said, I'm using that vertex form version to really make sense of what it is that we had. And I hope that that makes most sense out of that. Let me shrink that. Looks weird otherwise. It still looks weird, but that's all right. There's part C. Part D. Graph h of x equals f of x minus 6. So on this one, which one's f of x? This graph? So this graph is, wait, compare the graph to x squared. Okay, so I was making sure I did C correctly. So on this one, you have to think about what would happen inside of here if the original f of x, and as I said, this was, well, it was negative 2 times x minus 5 quantity squared plus 8. Now we're basically, there are 2 ways you can look at it. You can think about what the translation is itself, and I'm probably just going to sketch it on here, I don't know. But also, you're substituting x minus 6 in for x. It's taking x's place, and you got to see how that changes your transformation. So h of x is negative 2 times x minus 6 minus 5 quantity squared plus 8. Or negative 6 minus 5 is negative 11. So how does this graph change to the previous graph? It's translated, the vertex is now at 11, 8. So instead of 5, 8, it's translated 6 units farther right. Translate 6 units right of that other graph. That's all. So that's why I'm thinking about using this template that we have here. If everything can fit, maybe not really, but then I don't think everything could fit on my axes either. So I might as well just give it my best shot. I'm going to go ahead and do that. I'm just going to trace right over this thing, best as I can. Probably won't be very good, but I'll try. Then I'm just going to translate this thing over 6 units right. Give me one moment. You'll see what I'm about to do here. The important thing is you'd at least have the idea of what's going on with it. Whoops. Let's lock that one in. Okay. So this graph will be 1, 2, 3, 4, 5, 6 units over. Maybe that's not a good idea, but no matter what I do, it's going to be at that 11, 0. So it's going to be like that. So this graph here, I got to just move everything over. Sorry about that. All right, so it's going to kind of look like that. So this point is at 11, 8. There's this point, which looks like it's at 9, 0. That's 6 units to the right. And then there'll be another point over here that's 13, 0, which is 6 units over as well. Not the best look, but I just wanted to kind of get that one out of the way. There's nothing I could have done much better for my window range because, like I said, my graph's x's go from -10 to +10 and such. So that's on them for making the problem that they did. That's number 4. Number 5, use zeros to graph the function. Describe the domain and range of the function. So when they say use zeros, they're probably expecting you to get it into factored form or solve it by other means. Now, it's at this time, again, at the time that I'm recording this video, my problem is that I've already taught chapter 4. So I have to recall that in chapter 3, you haven't yet solved using quadratic formula, completing the square roots, and things like that. So we're just going to have to assume these are factorable, which this one looks like it is. I got a GCF of 2, and then I have x squared minus 4x plus 4 in here. Now, it says use zeros. I know that I recognize this as a perfect square trinomial, but for the sake of what I want to call zeros, I want you to fully be aware that these are, you know what, I'm not even going to call these f of x's for now. I'm going to go ahead and set it equal to 0. They're both x minus 2s. The bottom line is that for your zeros, there's only one of them. It's x equals 2. Now, that does mean that this graph does have a vertex on your x-axis. It's also the vertex, which is 2, 0. You know what? Maybe I should put 2x minus 2 squared. Sorry about this. Let's just do that. Because this is also its vertex form. Yeah, you know what? I want to redo everything I said. I can't undo this video, but I'm going to say f of x here, f of x here. Let's just redo that. I'm sorry about this. Now let's set it equal to 0. Because I want to graph off of that. Divide by 2. And you kind of have this guy right here. So you have x minus 2 equals 0 or x equals 2. There you go. I like that more. Okay. Now this is the vertex form. And this is what I'd be graphing off of. Do I need to graph it? Yes. Use the zeros to graph the function. Because this thing has its 0 on the vertex, I'm using the somewhat factored form, somewhat vertex form to make that happen. It's both factored and vertex form at the same time. So apologies for that. There's not much I can do on that. That being said, let's go ahead and do that. Let's put it at 2, 0, where that vertex is. It's also your 0. It's got a stretch factor of 2, so over 1 up 2, over 2 up 8. That seems to match the y-intercept of 8. And over 3 up 18 if you're doubling 9. There's one thing I'll miss about this chapter is that graphing and such takes quite a while to do. Maybe not the graphs themselves, but getting different forms and things like that. At least when you're teaching it. The domain is all real numbers. All these are pretty much expected to have all real number domains. Range is going to be y is greater than or equal to 0. Okay, that's number 5. Number 6 is already in its factored form or intercept form. So on this number 6, we have y equals negative x plus 5 times x minus 1. We're going to set this equal to 0. The negative has no bearing on these zeros solutions. Your zeros are x equals negative 5 and x equals 1. This time I can do significantly more when it comes to using these zeros because there's more than one of them. Last time the vertex was the 0, so I strictly used the stretch factor. as it was the vertex, I kind of treated it like vertex form as well. This one's a little bit different and a little bit more intuitive, where I use this -5 and this 1 as my two zeros. Now, your goal is to find the axis of symmetry, the halfway point in between these two. And the halfway point is found by averaging these, or literally finding that halfway point, what's half the distance and all that. So -4/2 is -2, okay? Being -2, x equals -2. There's a vertical line up and down here if you'd like to draw it as the axis of symmetry, which is not only where all the points reflect across, but also where your vertex exists. Let me fix that. Also where your vertex exists. We'd still have to find the y value for it, though. The y value is found by substituting in -2 for x into the original equation. It's also another way of finding vertex form if you wanted to. So this is the opposite of 3 times -3, which is +9. So your vertex is at -2, +9 up there. Now, this isn't written in standard form, so I can't see the y-intercept for what it is. I do have the stretch factor, though, the a value that's -1, and we'll confirm that we're at least going to hit those points there. So we get to go 1, 1, downward, 2, 4. Looks like that y-intercept would have been 5, which does make sense. If I expanded this, the constant would have been 5. 3, 9, which is these points here, 3/9 down, and 4, 16. Probably fit 25. Yeah, 25. That's at -16 here. 5/25 down. Oh, yeah. Okay. Big. But I did graph it from the zeros. I used the x-intercepts to determine all the stuff there. That's kind of the point. Now, I got to think about... Again, I don't think we solved using square roots quite yet in this chapter, so I'm going to revisit it as we know. Okay, domain, all real numbers. Range, y is less than or equal to 9. Okay, there's number 6. Number 7, h of x equals 16x squared minus 4. Okay. Using the zeros, once again, would probably require some form of factoring. Let's go off that. So, let's go ahead and factor. 16's big. That's our a value. This is going to be a really kind of weird graph. These are the ones that I was not generally a fan of. GCF? Yeah, there's GCF of 4. GCF of 4. Now... How do I want to say this? This won't be our factored form. This will just be factoring. This will just help us get our zeros. Your a value is 16. I need you to remember that. A is 16. It's not going to be 4, despite the fact that 4 is a GCF out of this, because I only get down to 4x squared minus 1 inside of here. As long as your factored form does not have x plus or x minus inside there, and there are other numbers other than x, then it's not truly factored form. My goal right now is strictly to get this solved for when y is 0. I want to find those zeros. So I'm going to, really this 4 doesn't matter anymore, but this is a difference of 2 squares, and it factors to 2x minus 1 times 2x plus 1. This is where you can solve for these two zeros here. 2x minus 1 equals 0. You add 1 to both sides and divide both sides by 2. So 1/2 is one of the zeros. And it looks like -1/2 will be the other zero. So these are your x-intercepts. Now remember, this wasn't true factored form. Not unless I factored 2's out of there, made that into 16, and called this x minus 1/2 times x plus 1/2. But I didn't want to factor that way. I especially didn't want you to see the factoring that way. You probably would have been a little confused on what I was doing. So I'm trying to avoid confusion. I also want to avoid confusion by saying that that's not factored form. So your a value will be 16, which is what we get to graph out of, but we still need to find the vertex. Now, the axis of symmetry shouldn't be too hard. These are at 1/2 and negative 1/2, which are like that. I could change the scaling, but I'm going to choose not to. 1/2 and negative 1/2, which means the axis of symmetry is on x equals 0, the y-axis. Axis of symmetry is x equals 0, halfway in between. Now we're going to substitute 0 for y. For x to find the y value. H of 0, I'm going to use the top equation. It's negative 4. 16 times 0 squared minus 4. So we have this point here. I guess I didn't, substitute. Look, the constant value, standard form also has your constant value. Constant value is the y-intercept. Y-intercept is on the y-axis, is on the vertex, which means it's going to be that. So that's cool. From here, there's really, all I can do from here is use my stretch factor over 1 up 16. 16 times 1. I can't do over 2 up 64 and fit it. So this is going to be a very skinny graph. It's going to basically look V-shaped. And I do want to hit those 1/2 and negative 1/2 values. So I'm going to try and just kind of skinny it into there and make it look like the best U shape that you could actually get, even though that's probably a false version of it. It's totally okay. It's just what I'm going for. Not loving the graph personally, but you know what? It is the graph. The domain, no matter how little it looks like it's going left and right, it is. Therefore, the domain is all real numbers. Goes forever left and right. The range is y is greater than or equal to negative 4. And that is number 7. Number 8. Oh, I forgot we did this in this chapter. Identify and focus. I guess the focus. Identify the focus, directrix, and axis of symmetry of x equals 2y squared. Graph the equation. Okay. X equals 2y squared. If you recall, x equals y squared equations are sideways parabolas. They're not functions. This graph is going to open to the right. It's going to be looking like that. The focus is inside of here. The directrix is outside of there like that. We'll be drawing an official graph, and I'm probably just going to be using a squared off graph for this one this time. I see no reason why using a tall graph would be helpful for me here. So I'm going to be doing one of these because it's a sideways parabola. I'll give you a little more stuff in a second. I'm just trying to fit this in. Now, if you recall the A value, let's see which way I want to put this. A is 1 over 4, B is 1. There's a P value that's the distance from the vertex to here and the vertex there. Now, this vertex happens to be on just the origin. There are no translations that we can see here. All right, 0 translations. And there's vertical stretch of 2. Listen, I could draw the graph right now if I wanted to. That's fine. But they did want us to get the focus and directrix. So, as far as the focus and directrix go, they are P units right and left of here. The P value is found by using 1 over 4a. 1 over 4a, or 1 over 4 times 2, which is 1/8. P will be 1/8, which I can't really draw these because 1/8 this way and that way are really tough to really show. But the actual focus is going to be at 1/8, 0. Inside on that side, boom, like 1/8 away. And the directrix will be a vertical line going like that. So the directrix is at x equals negative 1/8, like that. Drawing the graph from here, it's a horizontal stretch by a factor of 2, up 1 over 2, down 1 over 2, up 2 over 8, down 2 over 8, like that. Whoops, that's not down 2. And that's going to be the graph. I remember that section being very rocky when it came to the kinds of graphs they had us do, especially when it came to certain fraction bits, because we're getting like, I don't know, certain fraction bits. So, did I need anything else? Axis of symmetry. Axis of symmetry was, or would have been, y equals 0. Horizontal line going that way. Going that way. That might be the only question on focus directrix stuff. We'll see if there's a... Oh, nope. Right here. Numbers 9, 10, and 11. Write an equation of the parabola. Justify your answer. I probably need to copy and paste these over one at a time. So let's start with number 9. Okay. I'm not going to justify my answer. I'm just going to calculate things to get it. All right, number 9. First of all, it's a y equals x squared equation. This vertex, by the way, these are scaled by 2, so I think that's at -3, 2. -3, 2. And the focus is at -3, -5. So let's just begin with that. It's a y equals x squared equation. Y equals -x squared equation, more specifically. Our goal is to find the a value, as we actually know the h and the k so far. We know, or it's y equals a times x minus h, so x plus 3, quantity squared plus k, like that. The a value is found based on finding p. Now, a will be negative if you forget this part, but this distance here is p. It's the distance from your vertex to your focus, and it's going to be negative since it goes downward. So it's going from 2 to -5. That's -7. A is 1 over 4p, just like p is 1 over 4a. So 1 over 4p is 1 over 4 times -7, which is -1/28. It's these kinds of fractions I had to run into when it came to me graphing. But this is a total vertical compression, y'all, when it comes to this. That's why it looks so shrunk like that. So that's just going to be the look of it. So the final equation is going to be y equals -1/28 x plus 3 quantity squared plus 2. It asks me to justify it. I'd say that's justification enough for what I got on that. But that's going to be it. Number 10. Now, 10 I don't think is focus and directrix, centric. I think it just has more to do with what we have here. Number 10 is going to be a lot like number 4 when I wrote the function in standard form using vertex form. Let me kind of shift this up a little bit. So I'm going to use the same principles, only they didn't really label things for you. You're going to have to understand where things are just based on where they're plotted or how parabolas go itself. So on number 10, what'd they say? They just said write an equation of the parabola. They didn't say what form. Vertex form is probably generally the way you're going to be doing a lot of these. So these are scaled by 1s. That's 5, 3. This is just some point on the graph, just some x, y. I don't need the comma, just some x, y. Whereas here we have a vertex that looks like it's at 3, 4. The vertex is at 3, 4. That would be your hk in essence. So as far as an equation goes, this would be y equals a times x minus h quantity squared plus k, like that. And I'm going to use this 5, 3 as my x and my y to find my a. I could also do what I've done a lot with you guys in the past, which is just finding out how much I'm going over and down. So check this out. I'll show you both versions. When I go over 2, I'm going down 1. Excuse me. Normally when I go over 2, I go down 4. So the essence of this is that I'm taking what I would, normally I go up 4. I would take my 4, I'm multiplying it by some a value, some stretch factor, and it changes for me to be going down 1 instead. So what should that a value be? Looks like it's going to be -1/4. Now, that's my way of doing it. You don't have to write that if you know what you're doing with it. The other way of going about this, of course, is substituting in the y and x. X is 5, y is 3. So 3 equals a times 5 minus 3 quantity squared plus 4. I'm going to subtract 4 from both sides and get -1. I'm going to do 5 minus 3 to get 2. 2 squared, and you get -1 equals 4a. Hey, that looks familiar right here. Divided by 4, you get a is -1/4. So you can see where I got that same answer out from what I did in a different method. So your final equation will be y equals -1/4 times x minus 3 quantity squared plus 4. All right, there's number 10. Number 11, this one is a focus and directrix problem. Sorry, copying it. So number 11. Okay. Now, this one only gives you the focus and direction. Oh, excuse me. It doesn't give you the focus. It gives you the vertex. So on this one here, they do not give you the focus, but the directrix The directrix's closest point is the same distance away from the vertex as the focus would be. So this is also P, but P goes toward the focus in its positive direction. In other words, like this. This is an x equals y squared equation, but it is a positive y squared equation as it goes to the right. If it went to the left, open up to the left, it'd be a negative. The focus is over here. Now, they don't ask you what the focus is, but what the focus? The focus is over here, and this is where you get your true P value. P is positive in this direction, however far that distance is from there to there. So basically, P is a positive number. What's the distance from vertex to directrix? We're going from 2 to -2, which is 4. Not -4, but 4. So the P value is 4. Your vertex itself is at 2, 0. That's important for this equation. It'll be x equals sum a, which we still got to try and figure out, times y minus k. That's a y minus 0 quantity squared, and then plus h being 2. You have to remember that this is a k and h this time, not h and k. And you got to flip the k and keep the h the same. The a value is found by doing p is 1 over 4a. Excuse me, a is 1 over 4p. A is 1 over 4 times that 4, which is 1/16. Therefore, your final equation will be x equals 1/16. And I don't need the y minus 0. I can just say y squared plus 2, like that. I like it. Okay, number 12. How far does this go? Just to 16. Number 12. Tell whether the table of values represents a linear, exponential, or quadratic function. Explain your reasoning, then write the function. At the time of this recording, I did not make a video for this section. It might be section 3.7. I forget the sections by number at this point, but it's the final one in here. So at the time, I didn't make a thing. Maybe later down the line, I'll be able to do that. So that being said, I don't know how the book goes about teaching it. Something I'm going to apologize for. I'm just going to tell you what I recognize here. I can literally do tests on one thing versus the other. You can also probably recognize some of them for yourself as well. Especially when it comes to quadratics. We're going to have to talk about that when we see them. Linear functions would have a constant rate of change. As x increases constantly, so would y. This shows a difference of 4. This shows a difference of 8 and a difference of 16 and difference of 32, etc. These differences are not constantly. It's not a constant difference. If I added 4 each time, it would be constant. So it's linear, it is not. Linear, it is not. Exponential. Exponential is about, in some other ways here, this isn't always true because there could be a shift, but in integrated math 2, I do not believe you will see that shift. So for all intents and purposes, here you're looking at, is there a constant common ratio? Are you multiplying the same number each time here? In this case, the answer is yes. You're multiplying by 2 each time here. That does make this an exponential function. We'll talk about quadratic if they get there. It says then write the function. So again, I don't know what the book does here. I haven't yet done the video thing for you guys, but here's what I do know we can do. What we can do is come up with an equation in the form y equals a times b to the x power. That's what exponential functions look like. You can use, there's not much I have to, listen, I'm going to be honest, there's not much I have to do with this because they gave us the x-intercept and they gave it, the y-intercept, the y-intercept. And I don't know if they're always going to give that to you, but your y-intercept for a, we learned this back in section 1.6, I believe. Your y-intercept is a, so a equals 8 because of that guy there. B is your growth factor as x increases by 1. That's b equals 2. It's what you're multiplying by. So this equation will be y equals 8 times 2 to the x power. Now there's another way of going about getting that thing solved by plugging in some x's and y's and solving it essentially like a system. But because they gave us the information I need from it, that's what I'm going to use out of it. And until I determine otherwise, that's how I'm going to be doing those problems. Number 13. X equals, excuse me, let me copy and paste this. Not x equals nothing. Your x values are these. Your y values are those. Hold on. There we go. Okay. Go based off, is it linear, is it exponential, all that kind of stuff. Do you have a constant rate of change? I got +6, +2, -2, -6. No. Linear, it is not. Do I have exponential? Are you multiplying by the same thing over and over? In this case, also no. The very fact that you get to 0 would mean I'd have to multiply something by 0, or there'd have to be some sort of shift. But also the fact that you go back to numbers that you had before means it can't be that. That means if they're saying it has to be one of these three, it's going to have to be quadratic. Now, what deems this thing being quadratic? Let's go back to what I just mentioned about linear. This goes -2, and then this goes -6. This went +6 and +2. Notice how the difference has a common difference. From +6 to +2, you're going -4. From +2 to -2, you're going -4. From -2 to -6, you're going -4. When your difference has a common difference, it's known to be quadratic. When your difference has a common difference, it's known to be quadratic. When your difference has a common difference, it's known to be cubic. Things like that. It's just kind of, it's the next layer down, the next degree, if you will. Degree 1, degree 2, things like that. That can kind of confirm its quadratic nature. As far as an equation goes, I'm going to go pretty straightforward with this one as well. The vertex is at 0, 0. It's going to be y equals ax squared equation. If we're going over 1 down 2 over 2 down 8, that's a vertical stretch factor of 2. It's going downward. So y equals -2 times x squared. You can plug in some values and figure it out, but if you do know the pattern stuff that I do while graphing, that's how that's going to be used. Okay, number 14. You are playing tennis with a friend. The path of the tennis ball, I remember a lot of these questions with weird calculations. Path of the tennis ball after you return a serve can be modeled by this function here, where x is the horizontal distance in feet from where you hit the ball and y is the height in feet of the ball. Let's write that out and figure out what the heck they want us to know. Hopefully they don't say graph it. I don't even know what section this will be a part of. I guess standard form. Oh yeah, they had this kind of question. What's the maximum height of the tennis ball? Part A. So this is all about finding the vertex. Now, your vertex you can find out of standard form can be found using -b over 2a. -b over 2a. So that's -0.17 over -0.001, which I think that's a 3 decimal place shift over. Is that 170? I think that's 170 feet. That's not the maximum height. That's the distance where the maximum height is hit. Pardon me. This is not going to be -0.001. This is -0.01. I was going to say that is a long tennis hit even for being half the height. So this will be 17 feet. That makes more sense. Okay, 17 feet is not half the height. 17 feet is where the maximum height occurs. So the y value is -0.005 times 17 squared plus 0.17 times 17 plus 3. This time I'm going to whip out my calculator. You don't have to see what I'm calculating, but -0.005 times 17 squared. Probably should have used the calculator for the first one in case I made a mistake, but I don't think I did. Plus 0.17 times 17. I think that's 2.89. Plus 3. 4.445. That's exact. 4.445 feet. About 4.5 feet. They don't ask me to round, so I'm not going to. That's part A. Part B. You are standing 30 feet from the net, which is 3 feet high. Will the ball clear the net? Explain your reasoning. So we have to figure out, basically, trying to think again because we haven't solved quadratics using other forms other than factoring, which must mean this is somehow factorable, or I can use enough information from here based on the graphs. I'm going to think more graph-based based on what we've been doing. So part B, I'm going to think about it like this. The initial height of my, is this a serve or just a return? That's a return a serve. So I return a serve 3 feet in the air. 17 feet later, it reaches the maximum height. It reaches the maximum height of 17,4.445. That's neither here nor there as far as mattering. What matters is parabolas have symmetry. So another 17 feet later is 34 feet, right? At 34 feet, I should get this height of 3 again. 34, 3. And they're asking if at 30 feet there's a net there that's 3 feet high, will it clear it? The answer is yes. Yes, it will. Because it doesn't hit 3 feet of height again until 34 feet later, which is 4 feet beyond the 3-foot net. So yes, this will clear it. My visual and my verbal explanation will be enough for me for explaining my reasoning. Yes, it'll clear the net. Number 15. Find values of a, b, and c. So the function f of x equals ax squared plus bx plus c is an even, odd, and neither even nor odd. A little open-ended. I forget what section this was out of. It must have been that 3.3 or whichever one this is, where it's standard form. We need it to be even. To be an even function, you can't have a b value. That's basically the extent of what I need here. I need anything else. So I can make this 2x squared minus 6. I can't have a degree 1 term. I can only have even degree terms. I can't have an odd degree term. There's an example. These are open-ended. So you can come up with any number here and here. I don't think they want a to be, actually it might have to be. Never mind. I was going to say, I don't think they want a to be 0, but an odd function is going to need exactly that. You can only have, in this case, the odd degree term. In a polynomial, you must have all odd degree terms to be an odd function. You must have all even degree terms to be an even function. To be neither, you must have some combination of both, even if it's all 3 terms in this case. So I'll make up whatever. F of x equals x squared minus 7x plus 21. That's going to be a neither case. That's all that I'm really getting from that. All right, last one from the test portion, number 16. Consider the function f of x equals x squared plus 4. Find the average rate of change from x equals 0 to x equals 1, from x equals 1 to x equals 2, and from x equals 2 to x equals 3. What do you notice about the average rates of change when the function is increasing? Okay. So they said consider the function as far as like, I don't know if they want you to graph it, but I'm going to. 2 to 3, it won't fit on this one. I need to get a taller graph here. Now, I don't think you need the graph specifically, but I want to demonstrate for you not only that what we find is true to be the case, but I also want you to know what it is that we're even doing. 3, 9 up. It's right there. Okay. Average rate of change is a fancy way of saying slope. The difference is it won't be the literal slope on this curve. They will be virtual slopes going from one point to another based on where these points are. They're asking for average rates of change here from x equals 0 to x equals 1. So I'm going to simulate what this is basically. You're going from here to here, and they want you to find that rate of change that goes through those 2 points. Okay? So they're looking for that slope of this right here. Now, we could probably say what that is together visually, but we are also going to calculate it. So for that one, let's thin that out. you can see that you are rising and running 1. Now that's because f of 0, here, we're going to compute all these first. F of 0 is 0 squared plus 4, which is 4. F of 1 is 1 squared plus 4, which is 5. We have these on the graph. F of 2 is 2 squared plus 4, which is 8. And f of 3 is 3 squared plus 4, which is 13. Once again, I believe they probably wouldn't have had you graph this, otherwise we'd see those answers. But for that first one, we're trying to figure out the average rate of change for that one, and that'll be the rise over run, your y2 minus y1 over x2 minus x1. How far do we change in y from 4 to 5? How far do we change from 0 to 1? And you get a slope of 1, up 1 over 1, and that seems to agree with what that is right there. The second one, it goes from x equals 1 to x equals 2. What's that average rate of change? And once again, you can see the visual. I think that goes back to the whole point of we probably wouldn't have drawn this graph to answer this question when they say, what do you think happens from one to the other? Clearly, it gets steeper, as you see on the parabola. But that average rate of change there, we're going from this change from 5 to 8, and as we go from 2 to 1. So this slope is 8 minus 5 over 2 minus 1, which is 3 over 1, or a slope of 3, which seems to agree with this from here, up 3 over 1. And then the last one, what color? Guess I'll just go with purple. The last one, we're going from x equals 2 to x equals 3, right? Is that what they wanted? Yeah. X equals 2 to x equals 3, so you're looking at this slope right here. I don't know if this is perfect placement of slope. I'm just kind of giving the idea. That would be up 5 over 1, but to confirm that, we're going to go with a slope. Whoops, let's change the color. Go with a slope. I don't know what section this is out of. Once again, I can't remember where this was used. But 13 minus 8 over 3 minus 2, which is 5 over 1, or 5. So we can see the slope is increasing, the average rate of change, excuse me. So what do you notice about the average rates of change when the function is increasing? The average rates of change, they're also increasing, but they're also increasing by a constant amount. Increase by 2 every time. This goes back to what I mentioned about the difference has a common difference. And remember when I was doing these problems right here. Now these ones changed by 4, -4 because the graph went downward, but also because it was doubled, right? These ones would naturally change by 2s. The change has a change. The rate has a change there, and that's what's happening there. Okay, so that's for the test portion, all right? Now we're going to move on to the cumulative assessment portion. So we'll see which things they're out of. Hopefully I can point out even what section they're from if I remember. Unfortunately, I'm so distant from remembering exactly each section that maybe I won't know. I think I'll know out of chapters 1 and 2. Chapter 3, it's actually a blur because I don't remember which ones had standard form, intercept form, all that kind of stuff. Okay, so let's move forward to these ones here. There will be 9 questions. I believe a lot of them end up being multiple choice. So number 1, which function is represented by the graph? These are scaled by 1s. Okay, it's not going to be A or B because those would represent upward facing graphs. It looks like it will be C based off this vertical compression that we have here. I'm just kind of answering it right here. They don't even ask me to explain why. Over 1, down 1/2. Over 2, down half of 2. This one would have been a vertical stretch, so not quite there. So number 1, that answer is going to be C, y equals -1/2 x squared, without actually drawing it. Number 2, a linear function f has the following values at x equals 2 and x equals 5. I'm sorry, before I go back, on number 1, that was probably from section 3.1. That was probably from section 3.1. Number 2 is probably inverses. Is probably from section 1.3. Speaking of inverses, it's probably from section 1.3. So f of 2 equals 6 is another way of saying I have an ordered pair that is 2, 6. When x is 2, y is 6. And then f of 5 equals 3 is another way of saying I have an ordered pair that's 5, 3. They say, what is the value of the inverse of f at x equals 4? In order for us to do that, we'd have to come up with an equation for this thing here. Well, I guess we don't have to. We can come up with the drawing and figure out if there's a certain slope that we could come up with that as well. But I think I'd rather kind of come up with an equation. I'm trying to think, because this is a different kind of question you would have been asked. We can use point slope form or slope intercept form. Well, what's the slope? You know what? Let's just draw it, because you guys wouldn't have done like these different equations. You wouldn't have made up an equation of your own. So that's why I kind of want to do that here. Okay, so for here, I have a point that's 2, 6 and 5, 3. This is the original function. That looks like it does have a slope of -1. Let's sketch that graph. You know what? I could come up with the equation now that I have the sketch of the graph. So I'm trying to decide whether we should talk about that or just sketching the inverse and going off that. Why not do both, Mr. Robinson? Yeah, good idea. Just trying to get that -1 slope sketch taken care of. There we go. Oh, the inverse graph is the exact same thing, though. See, when you have the point 2, 6, its inverse would have 6, 2. That's right there. When you have 5, 3, this is the point 3, 5. Its inverse graph is the exact same, which is kind of weird. So if I want to talk about both things, f of x equals, this is an equation that's -x plus 8. If I substitute y, if I turn this into a y, and then I swap x and y like that and solve for y again, I get to subtract 8 and then divide everything by -1. I get -x plus 8 all over again. So the inverse graph is the same. Well, that's no fun, but that is what that is. Now they say, what is the value of the inverse of f at x equals 4? So I want to make sure that they that I substitute 4 into here. I believe I do. So inverse of f of 4 is -4 plus 8, which is 4. It's going to be the same answer no matter what. 4, 4 would be the one. Kind of a screwball-y question, because you get the same answer no matter what. If they said, what is the value of f at x equals 4? You'd still get 4. So doesn't really matter, but that's what we got. All right, number 2. Funny. Number 3. The function f of t equals -16t squared. Let's see. F of t equals -16t squared plus v naught t plus s naught represents the height in feet of a ball t seconds after it's thrown from an initial height s naught in feet with an initial velocity v naught in feet per second. The ball reaches its maximum height after 7/8 of a second when it is thrown with an initial velocity of blank feet per second. Okay. I'm going to go with vertex form. I want to think about this one. If I do vertex form, after 7/8 of a second, I'm trying to think. If I substitute 7/8 into here, that doesn't get me a full picture of anything because I don't have any information. Let me read that again. T seconds from an initial height velocity v. Ball reaches its maximum height after 7/8 of a second. Okay, I know what to do. The vertex, we're going to use -b over 2a. The t value being -b over 2a, it's -v naught over 2 times -16, which ends up being 7/8. That's the part that ends up being 7/8 after calculating. So I don't even have to use the s naught portion of this. I'm just referring more so to this equation and solving for v naught from there. So this equation can be written better as -v naught over -32, or positive over positive, right? Positive V naught over positive 32 equals 7/8. And do what you will on this. I'll just go ahead and work off cross multiplication. So 8 times V naught equals 224, I believe that is. Divide both sides by 8, and you get V naught equals... I have trouble with these. 28, I think. I'm going to check that. Yeah, 28. 28 feet per second. So that should be the answer to that guy. So again, I use negative b over 2a for that portion. There's maybe some form of vertex form I could have used, but I wouldn't know my k. So the point is I'm not trying to get the k even out from this. I'm strictly using the x bits. So that'll work out. Okay. Number 4. Oh, what section would have been that from? Vertex standard form. I'm guessing that would have been out of 3 point. I think that's 3.3 that does that. I believe. I really got to look at my section. Hold on. I'm looking at my sections right now. Chapter 3. Yeah, I think that would have been 3.3. Vertex form is 3.4. Intercept form is 3.5. So, okay. Number 4. Order the following parabolas from widest to narrowest. All right, A is going to take the most work. The other ones are going to have to kind of do their thing. A has a focus of 0, -3 and a directrix of y equals 3. For this first one, imagine a graph. Now, they don't care. I don't think they care about what are x equals equations, what are y equals equations, what face upward, what face downward. I think they're just referring to A. Because I don't know how to explain how a left to right graph is more or less wide than other ones, other than how it is relative to its own direction. Anyway, for A, this graph goes in that direction there. That's not relevant. All they care about here is the p. In this case, p is -3. So A is 1 over 4 times -3, which is -1/12. So what I got to do is compare. So the equation is y equals -1/12 x squared. So what I got to do is compare A to B. They just say from widest to narrowest. I really don't care about anything else other than these values here. And not even the negative part. I just care about that, x equals 1/8 y squared, that, and this, y equals 1/4 x plus 2 and this. I just got to be sure when thinking about the 1/8 y squared, it will be instead horizontally compressed. I mean, they're all compressed in their own way, but I'm trying to think if we argue width going left right versus relative, because you know this is wider, but is this also wider? I'm going to assume yes, because I can't otherwise compare something relatively that direction for an x equals equation. I'm just going to have to work with that. From widest to narrowest, you're looking at the ones that are most vertically compressed to the ones that are least vertically compressed. So in order from widest to narrowest, I'm looking for the smallest number first, and then going from there. So it'll be B, A, C, and D. That's how I'm going with this. Hopefully that makes sense with what I said. And hopefully that's correct. Okay, number 5. Oh, that section would have been, well, that's a culmination of sections. So that would have been definitely 3.6 that does the focus parabola stuff. So that would have to be needed. I'm going to just majorly call that 3.6. Number 5. Which polynomial represents the area in square feet of the shaded region of the figure? Let's go ahead and copy paste that guy in and see what I have to say to manipulate that stuff, if at all, or write on it. although I do know the answer. So for this here, we're talking about the shaded region only. The whole length here is x feet. That small guy being a feet means that a can be taken out of these x's here, and this would be x minus a. This here would also be another x minus a. So the shaded region area is x minus a quantity squared, which simplifies to x squared minus 2. Do they do ax or xa? ax plus a squared. And that's looking like C. C being that answer. Now that section would have been out of chapter 2. That probably would have been 2.3. I'm going to guess, because that's special cases of things being a square. That's my guess of what we're looking at on that one, number 5. Number 6. I got 4 more questions. Number 6. Consider the functions represented by the tables. We just kind of saw some things like this before. Classify each as linear, exponential, or quadratic. They don't say to explain, so I'm not going to. Order them from least to greatest according to average rates of change from 1 to 3. Okay, that's just about finding slopes after that. So let's see if I can just kind of plop these in and identify them with y'all. Okay, so the first one, P of x, seems to be subtracting 12 each time. That would make this thing linear. Linear. The next one, you add 15, then you add 25, then you add 35, which means those have a constant rate of plus 10 and plus 10. That makes this quadratic. Remember, the difference has a common difference. Quadratic. Tick, 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 tick. I guess they did the constant rate of change stuff in that section. Again, I haven't covered it yet. These ones are dividing by 2, but you want to say what you're multiplying by instead. You're multiplying by 1/2. That's kind of how exponentials work. They're not asking for equations here, remember. This is exponential. This one has minus 8, then minus 16, then minus 24, which means these are becoming 8 smaller than they were before, which also makes this one quadratic. Bound to be a repeat on one of them. In this case, it was going to be quadratic that has the repeat. So those are the 4 different ones. Now they want average rates of change for each of them. For P of x, I'll just put P. Well, P of x. The average rate of change from 1 to 3 is going to be this guy. So negative 40 minus negative 1, P of negative 1. So negative 16 over 3 minus 1. Again, 3 minus 1 is going to be 2 each time there. Negative 40 minus negative 16 is negative 24 over 2, which is negative 12. For R of x, we're going to be getting a slope of, or average rate of change here, 40 minus 0 from 3 to 1 over 3 minus 1, which is 40 over 2, or 20. I'm going to box these. What are we averaging from, or what are we ranking from? Least to greatest. I'm guessing they mean smallest negative to largest positive, or whatever, if that makes sense. The third, oh, these are different, and these are the same color. I need to make them different. Seems like this red. The third one, S of x, we're going from 1 to 3, that's 18 minus 72 over 3 minus 1. Which is negative 54 over 2, or negative 27. And then the last one, 3 to 1, negative 5 minus 3. This is what? T of x. I didn't really write this part correctly here. Let me kind of fix this. S of x, sorry about that. All right, T of x, m equals negative 5 minus 3 over 3 minus 1, which is negative 8 over 2, or negative 4. Averaging from least to greatest rate of change, you want the super large negative, like, S of x. So S of x is the least, because it's going down. Least to greatest. Sorry about this. I want to color code. I want to write some things. Least to greatest. S of x. Then M of x. No, P of x. I just saw the M. P of x. Then T of x. Then R of x. It's possible that they were looking at just like negative 4 is the smallest absolute value, therefore. But if you're going downward for something, that rate of change can't be very good, depending on something. Maybe you're losing money, I don't know. Now for these, that was just from 1 to 3. That's not to say that that rate of change would be the same everywhere else on these functions, especially since some are linear, quadratic, exponential, etc. Exponential will take off more greatly over time. Actually, it's decaying, so maybe it won't. Okay, that's number 6. Number 7. Which expressions are equivalent to... Oh, that section was likely 3.8. Wait, 3.7. 3.7. Which expressions are equivalent to 14x minus 15 plus 8x squared? Excuse me. So, first of all, I'm going to rewrite this thing in standard form. 8x squared plus 14x minus 15. And looking at the selections, it looks like this is factorable, potentially, right? My goal is to try and factor this thing out. There's no GCF, but this will factor into some 4x times 2x. And I know this because of the even coefficient. These have to have even factors here. That's just a thing that I know. This may be a plus, maybe a minus, not sure. I'm not looking at the selected responses. I'm going to try these. I'm likely going to go for a 5 and 3, shoot for it, or switch them. Negative 12 plus 10 is not negative or positive 14. Let's swap that. Negative 20 plus 6 is negative 14, so I want positive 14, so I'm going to switch these guys like that. This is the factorization. So this is equivalent, and this is equivalent. I'm going to find those two and see if there's any reason to find anything else that'll work out of that. As far as section goes, this should be 2.6. That's where we started doing factorization of that kind. Excuse me. So 4x minus 3 times 2x plus 5. Not that one. Not that one. Standard form, no, not quite. It was this. And not that, and yes, this. So these are the two that are equivalent to that there. Okay, 2 more. Number 8. Complete each function using the symbols plus or minus so the graph of the quadratic function satisfies the given conditions. Okay? I have a couple yawns in me. You have to give me a second. Sorry. Okay, so I need blanks here. Oh, for the vertex be negative 3, negative. Okay. So vertex, I thought there was going to be a lot more work on this. Negative 3, 4. Okay. So for negative 3, 4, I want a plus there, and I want a plus here. The negative 3 for that, and the 4 for that. Yes, yes, yes. I want to use a different color. That might not show up blue enough for you. Plus and plus. All right, part B. G of x. This is the intercept form or factored form. X blank 2 and X blank 8. You have X intercepts of negative 8 and 2. For negative 8, remember when you set this equal to 0, you kind of get the opposite sign effect. So this is going to be a plus. Same thing here, opposite side. That will be a minus. This looks like out of several sections, by the way. I'm going to see what all the sections are after I do all of them. Maybe I can write them down individually. Part C, h of x equals some blank in front of the 3x squared, and then blank 6. The range y is greater than or equal to negative 6. This shifts downward 6 units. That would be a minus as a result of that. This thing greater than or equal to -6. That means this would be a plus sign because it needs to go upward to stay above it. So when we write equations, this is implied to just have a plus. You wouldn't have to write it. To fill in that blank, we're going to have to. So that'll have to show a plus right there. And then part D. Good thing I'm almost done. I'm going to yawn myself out. J of x. I'm not even tired. I'm just yawning. Blank 4. It's probably going to be negative this time. Another factored form, but they're asking you a different question out of this factored form. So range is y is less than or equal to 4. To be less than or equal to, this would have to stay negative. Now, the thing about this part, these just got to be opposite signs. One has to be a plus, one has to be a minus. And the reason for this is because if they were the same sign, that means that you'd have a 0 and only a single 0 at x equals one of those values. A positive 1 or a negative 1. That'd be the vertex, which means it would never hit 4. It would never hit 4 as its maximum height. So they just have to be opposite signs, whatever these things are. I like that question as far as that goes. Last question, number 9. Before I hit those, let me just write what these things would have been out of. Let's try and be specific. This would have been out of 3 point, I think it was 4, which has the vertex form. This would have been 3.5. This would have been 3.2. And this also should have probably been 3.5, all depending on what you're trying to do with it, just because it's in intercept form. All right, number 9, which expressions are equivalent to b to the -5th to the -4th power? This was properties of exponents. This is 1.4. So, last question, number 9. B to the -5th and the -4th. Okay, there's more than one way. I'm going to go through all the different ones that they have. I'm just going to copy and paste this over and cross it out or do whatever, because it's not there's more than one way to do this problem. There's more than one way to express what you have, right? When it comes to simplification, generally the goal is to get... they're both negatives. I was going to say, generally the goal is to get positive exponents, but a negative cancels out another negative. So okay. I thought there was going to be a fraction answer. Anyway, I'll write one part here. This is equivalent to multiplying these two things together like that, right? So b to the 20th will be one of them, but there's probably other things that you write in between. So -20's out. However, I guess that's out as well, but those would have added together. This works. This is equivalent because you would still multiply those two. So that one's fine. This one, no. That doesn't give you 20 either, so no. That doesn't give you 20, no. This does give you 20 when you multiply 10 and 2. This is the simplified version of the answer here. That would give you -36. And this is where you would actually get to add those exponents. 12 plus 8 giving you 20. So that is equivalent. That's why I said, especially this guy, everything really but this one are ones that I wouldn't ever go to as answers on my own when it comes to simplifying, right? But it does work out. That'd be section 1.4. All right, guys, I had my calculator handy. I did use it once when I did that one multiplication. But other than that, I didn't have to use it, and I didn't have to show you anything there. So that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I know this is possibly out of sequence. Maybe you were waiting on this video, or maybe you're brushing up for some other things. But in which case, I'm glad to have done some stuff for you. Keep posted for other videos upcoming here. Take care. I will see you in the next one.